So let's go to the next contributed talk by Alexander Thomas Gagliano on ELAsTiCC, a catalog of simulated transient-host-galaxy correlations for upcoming time domain surveys.
Yes, hi everyone. Hopefully you can see this okay. And the name of the catalog has changed somewhat, but the major results are still the same. So I'm going to be presenting on the simulated catalog of optical transients and correlated hosts, the catalog we are now calling Scotch. I'm an NSF fellow at the University of Illinois and now a pre-doc fellow at the Center for Computational Astrophysics. And I've completed this work in collaboration with Martine Loken at the University of Toronto. And so in this talk, I'll explain briefly the motivation for this catalog, how it was constructed, and how it's going to play a critical role in developing software infrastructure for transient studies with upcoming missions such as Roman and Rubin. For those of us who study transients from an observational standpoint, I would argue that the ultimate goal is to weave a connecting thread from some observed phenomenon to an underlying physical system. And with a greater understanding of that physical system, you can then construct a predictive model that will allow you to run the clock either forward or backward, far from the time of the observed phenomenon. If you're running the clock backward, typically you're interested in connecting late stage evolution of some system to the explosive transient. And the ideal way to do this would be to look for direct detection of progenitors or pre-explosion emission. And if you're trying to run the clock forward, typically you're interested in predicting how the transient will evolve, and classification through spectroscopy can get you most of the way there to doing that. But neither of these pieces of information, of course, will be available for the vast majority of transients discovered by upcoming surveys. And so the time has come to look for information that is both A, readily available for upcoming sources, and B, has some kind of predictive power. Turns out that host galaxy information or contextual information has both of these things. I think Sebastian already motivated this point pretty well with the features used by Fleet, but you can see the plot at left here showing the cumulative fraction of transients as a function of the stellar masses of their host galaxies from DES. And most revealing about this plot is that the hosts of superluminous supernovae, this pink line here, show a preference for lower stellar masses than the other transient hosts in this sample. And you see the opposite for type 1a supernovae, this green line here. You see a dearth of type 1a events in low mass hosts here, and then a large jump as you get to higher stellar masses. And correlations have now been identified for both directly observed and derived host galaxy properties for both a range of common and rare classes. And with sufficient software, we can further investigate and take advantage of these correlations as new data comes in. So the first work to develop this framework for simulating millions of realistic transient events was PLASTiCC, the Photometric ELAsTiCC Astronomical Time Series Classification Challenge. It's a mouthful. The PLASTiCC data consisted of 3 million ELAsTiCC-like light curves up to redshifts as high as 3 and was simulated using the SNANA simulation code. And for the challenge, full phase light curves were provided to the public on Kaggle, and the goal was to classify as many as possible. So here's an example event at left in this inset box, pulled from a paper presenting a classifier constructed with the synthetic data. It's important to note that the PLASTiCC data didn't contain any host galaxy correlations. Galaxies were instead matched at random within a given redshift range, and the photometric redshift was reported. And on the right, you can see a breakdown of the training set that was provided in PLASTiCC, which consists of a litany of both galactic and extragalactic transients. Now, to extend this initial framework, we've constructed Scotch, a catalog of 5 million transient light curves extending to redshifts as high as 3, and the realistic properties of their host galaxies based on a data-driven approach that consolidates what we know about these transients from extant samples. The Scotch catalog consists of a series of transient correlations with host galaxies, and the goal is to have it serve as a benchmark for investigating statistical samples of transient hosts for years to come. On the right, you can see the class-specific breakdown of the catalog. And I should note that because this is a truth catalog, the relative fractions of each event are not meant to be physical, but the relative distribution of each class as a function of redshift is realistic. Next, I'm going to provide a very basic overview of how we've encoded correlations with directly observed properties using GHOST and COSMO-DC2. So as with plastic, the vast majority of other synthetic transient data that have been generated, we use the ELAsTiCC simulation code. We start with two primary data sets. One is GHOST, shown here bottom left, and this is a data set comprised of about 16,000 host galaxies of different supernovae and their photometric properties in pan-stars. On the right is COSMO-DC2, which is a synthetic catalog that extends out to much higher redshifts. And so we use an approximate nearest neighbors algorithm to convolve the properties of these two catalogs, which give us the host galaxy correlations from GHOST and the increased survey depth and size of COSMO-DC2. And this allows us to arrive at 4 primary host galaxy libraries that we use for association here. 3 of these are supernova host galaxy libraries with correlations as they appear in GHOST. And we've grouped rarer classes like TDEs and Kilonova into a final library bottom right, which just comprises one random but representative subset of COSMO-DC2 galaxies. And for these classes, we encode correlations using a different approach that I'll describe next. So the final piece in encoding host galaxy information in Scotch catalog comes in the form of a weight map. Probability density function that weights the associations of transients in ELAsTiCC. So for every transient event that's simulated, the code searches the host library for all candidate host galaxies within some redshift window. And it then weights the association of host with transient by the properties specified in the weight map. And this allows us to encode theoretical correlations from literature, as well as correlations with derived properties like host galaxy stellar mass and star formation rate that are not reported in the GHOST catalog. And with these two components, the combination of the host lib and the weight map, we are able to correlate transients with a wide range in host galaxy properties from extremely low redshifts all the way out to redshifts of around 3. One of the primary science drivers for almost all of the upcoming time domain missions is to discover and study the second Kilonova event. These transients are extremely red because of the abundance of heavy elements and extremely rapidly evolving, so they're easy to miss. Host galaxy information can aid in rapid classification, but having only discovered one event to date, we don't really have a thorough understanding of the environments in which kilonovae occur. So for this class, we consolidate, we being myself and Laura Sallow, a PhD candidate at the University of Minnesota, we consolidate a sample of short GRB host galaxies, which we then use as a proxy for kilonova host galaxies, under the assumption that they occur in similar environments based on the association of the two types of transient class from GW 170817. This allows us to use the photometric properties of sGRB hosts to construct a kilonova weight map and encode correlations for this transient class in a synthetic sample. So here are results for 6 transients in the Scotch catalog, 4 supernova classes, as well as kilonovae and active galactic nuclei. Here I'm showing the selected host galaxies colored by redshift of the transient. Red points are higher redshift, blue points are lower redshift, as a function of the star formation rate and the stellar mass of the host. The most obvious feature of these plots is that you can see the host galaxies are different in this derived property space. So the final correlations with each host actually do tell us discriminatory information about the transient event itself. And we can also go through and look for specific correlations from literature and see whether we see the same properties in our synthetic sample. So if we just highlight these 3 classes here, we see a few prominent features. Hydrogen poor superluminous supernovae are shifted toward low mass galaxies and highly star forming galaxies. There are a couple of different studies that back this up. Core collapse events find a preference for active galaxies relative to passive ones, and AGN preferentially occur in massive galaxies. These are all correlations that now exist in the Scotch catalog. I want to spend just 1 second talking about the sampling of the light curves within the catalog. So again, this is meant to be a truth catalog. So the photometry that we provide is extremely high cadence. So we provide 2-day cadence for almost all classes, but there are a couple where we use a variable cadence that increases the sampling near peak for rapidly evolving events like Kilonova, so you can still resolve that curve. These data points are also meant to be top of the galaxy, so we don't simulate any Milky Way extinction or any atmospheric effects, but we do include host galaxy extinction such that effects of upcoming surveys can then be placed on top of this catalog to simulate synthetic observations for a variety of different upcoming surveys. And so just to end on a note for the landscape with Nancy Grace Roman, there are many different correlations at higher redshifts that remain poorly constrained. And this catalog, because it's the best we have, is mainly an extrapolation of correlations that we've observed and correlations that we believe to occur at higher redshift. But as upcoming surveys like Roman continue to find transient events at higher redshift, here's just a prediction of how many we think we'll find at redshifts of greater than 1. We're going to learn a lot more about some of these correlations that will allow us to revisit our current understanding of the connection between transient and host. And also, the near IR capabilities of Roman specifically will allow tighter constraints. There was a paper that came out of arXiv last night that found that at higher redshifts, we underpredict the stellar mass of the host galaxy because the UV data, which is redshifted into the near IR, is poorly constrained when using just optical. So hopefully near IR information for more hosts get us better derived components and can give us a better understanding of these correlations. And so I will end there. This paper is now in collaboration-wide review, and I'll take any questions you might have. Thanks very much.
Thank you very much. There are no questions yet, so I think I will ask my first question again. And that is, are these correlations so strong that you can also use these correlations to maybe trigger quicker or faster follow-up of a transient based on these correlations, to have like, okay, this is now really, we don't have the full understanding, but based on the host galaxy, I'm going now to trigger follow-up.
Yes, exactly. So the whole motivation for using host galaxy information is that it reduces the reliance upon photometric information from the explosion itself. And there are a few papers that are coming out recently that find that we can actually classify different transients pretty well using only 1 or 2 data points from the explosion and a variety of different host galaxy information. So yeah, that's a big driver for this research.
Do you have any quantitative estimate on the false positive on those predictions then?
That's a great question. I will just highlight the ELAsTiCC challenge. So this is the extended ELAsTiCC astronomical time series classification challenge. And the goal is to develop software architecture that can leverage this host galaxy information for faster classification from an alert stream. So we don't have quantitative estimates for that just yet, but all of this architecture was built up such that we have a training set for developing the type of models that will allow us to do exactly this. And hopefully we'll see some initial results from that within the next couple of months.
Okay, thanks a lot.